is assigned, so.
Okay, good.
Thanks though, Karen. I just sent you a text too.
Okay, good. So
Thanks, Karen.
I'll just be eating my breakfast here.
Okay. So Lori, do you think we should start? Or give people another minute or two?
Yeah, I guess it doesn't hurt to start a minute or two late.
Okay.
Yeah.
I'll just try not to go too many minutes over.
No. Right.
So I guess the challenge is somebody has to give me permission to share my screen.
Yeah.
So.
Oh yes, I've made you the co-host already, so
Oh, I'm already. I'll go ahead and share my screen then. Thank you.
Okay. So yeah, we may as well start, I think.
Yeah, I can see all the students are back.
Let's see. Oh shoot. I imagine you're seeing my outline. Let's see. There we go. You should be able to see it now. All right, are we ready to go?
There we are.
Yeah.
Okay, shall I just start, Lori?
Yeah, may as well. Yeah.
Okay, all right. Well, I am the lead off here. I'm going to be talking about basic concepts, and you can view this as kind of like an airplane flight over the world of verification, where you're going to see a lot of concepts and ideas that underlie verification. But you'll hear a lot more about many of these topics in detail in the subsequent lectures. So if you don't catch all the details or understand everything that's going on, understand that you will hear more about many of these things. So as you can see, this is like a big shopping cart full of ideas. Basic concepts includes a whole range of things, starting with what is verification, and then going to talking about statistical basis for verification, and ending with talking about meta verification and maybe some questions to ponder as we put together verification studies. So one of the great things I think Barbara alluded to in her presentation was how far the verification community has come over the last couple of decades, because we've had this really amazing focused group to think about many of these things. So some of the things I'll be talking about are things that were developed way long time ago, but many of them are things that we've really thought in a much more deep fashion in the last couple of decades. So just to start with, I think somebody's not muted. Getting a little feedback there. Okay, so just the very basic question, what is verification anyway? And so I start out with a definition from a dictionary of what does the word verify mean? And basically, if you look that up in a dictionary, I don't know which dictionary I found this from, but to confirm or substantiate in law by oath, or to establish truth, accuracy, or reality. And that seems to be what we try to do when we do verification of forecasts. So it's the process for us of comparing forecasts to relevant observations, and the word relevant observations is really important because in order to have meaningful verification, you have to have meaningful and representative observations. And verification is one aspect of measuring goodness. And it measures essentially the quality of the forecasts as opposed to their value. But for many purposes, because of the way we do forecast verification, and we look at things in a more in-depth way, we're not just trying to, the idea is not to get a single number that's going to summarize everything, but we're looking in a more broad way. And so for a lot of purposes, it's more appropriate to say we're doing evaluation of forecasts. So in my mind, those terms are not exactly interchangeable, but I think evaluation embodies something a bit bigger than verification itself. So why do we do verification? And the traditional definition of verification came from a chapter in a book that Breyer and Allen wrote in 1951. And I think these three purposes still kind of stand today, is why we want to think about doing verification. And they are economic, administrative, and scientific. And I thought it was interesting. I went back to this paper to look, and that's the order that Breyer and Allen presented their list of the purposes of verification. I think it was probably very relevant for the times. So when they talk about the economic purpose, they were talking about things like the justification for investment in weather and climate services. But we also think for an economic purpose of understanding what is the value of the forecast, how does it increase value for the users? It also has an impact on improved decision-making and related to that, feeding decision models or decision support systems. The administrative purpose is more related to looking over what the forecasters are doing, if you have human forecasters in the loop, or how the NWP forecasts are performing. And it can be used also, for example, to choose a model or a model configuration to determine whether, are we really making improvements in the forecasts overall over a period of time. So there's a lot of verifications for the purpose of tracking performance of NWP models over time. The scientific purpose is probably what is of most interest to this group at this point, at least. And it's, a way of looking at models and identifying and correcting their flaws and evaluating whether we're really making improvements in forecasts. Developing ways to understand how our science is actually changing or improving things. So there are a bunch of other reasons that you might want to verify forecasts. And for example, you might want to help operational forecasts understand the models that we're providing to them. So this is in an operational setting. How do we help them select models to use in different situations? And also helping users who, and I don't think we've really reached out to users very well with this, but it could be used to help users interpret forecasts. So for example, what do I really mean when I create a forecast of 0 degrees, where I produce a forecast saying it's going to be 0 degrees tomorrow? Is it going to freeze or is it not going to freeze? And we know from our experience in weather forecasting and climate prediction that 0 degrees does not necessarily mean exactly 0 degrees. And then finally, to identify forecast weaknesses, strengths, and differences that help guide research and help guide improvements to forecasting processes. So the first step in doing a verification study is to identify what the goals are. And associated with that is simply understanding what questions we want to answer as we go into a verification study. So we might want to look at where does a model have the best performance, or where does it have the worst performance in a place where we need to figure out why it's not performing well. Are there certain regimes where we have better forecasts? So does, in our case, the WRF model, or does a WRF model work better in summertime thunderstorms or in winter storms? And understanding those kinds of differences in variability and performance. If we're doing probability forecasts, we want to know if the forecasts are well calibrated. Are they reliable? Can you interpret a 20% probability as actually a real probability of 20% that something will happen. Another example would be whether we are capturing the natural variability of the weather. So you might think of some other examples as you think about this presentation, or as you're sitting here, of what the goals might be. And you may have your own goals as you think about applying forecast verification techniques. Another important aspect of this is deciding what is it we really care about in terms of performance. How do we measure them, and what exactly should we be measuring? And that's related to the question that we're asking about forecast performance, as well as the kind of forecast and observation. So the way that we evaluate performance is related to all of these things, what it is we want to know, as well as the kind of forecast and kind of observation. So the choice of, there's a wide range or array of verification statistics, measures, graphics, and you're going to hear about a lot of those during this week. But the choice of those that are used in any kind of study of evaluating forecast systems needs to match the kind of forecast, as well as the attribute of interest and the observations that are available. And it should measure the quantity of interest rather than trying to infer something. So we have to match the questions that we have to the quantity that we're trying to evaluate. So it's a process of figuring out what is the best way, what is it I need to do to answer the question I'm interested in. So now I want to talk a little bit about what we mean by forecast goodness, because that's what we're trying to evaluate when we do verification. How good is the forecast? And that goodness depends both on the quality of the forecast as measured by verification techniques, as well as how the user applies that information, the forecast information. What is it that they're really interested in learning from a forecast? Here's an example, and you're actually going to see this later in the week in the context of the spatial verification talk. But we have this situation on the left. We have the orange oval, that's the forecast area. We'll think of this as a geographic region. And the blue one, which is the observed area. And you would look at that and you'd say, well, that's a terrible forecast because there's no overlap between the forecast and observed. So many verification approaches that we apply in using standard methods would say that this forecast has no skill, and it's totally inaccurate. But it depends on who you are. And if this is an example where I've overlaid a map of a watershed, and if I'm a watershed manager for this watershed, it is a pretty bad forecast. So the rain actually fell, if we think of it as a precipitation forecast, the rain actually fell right over the watershed, whereas the forecast showed the rainfall happening to the west of the watershed. But on the other hand, if you're just trying to get an airplane from point A to point B, and you just need to know, am I going to run into bad weather on my route, then it might not be such a bad forecast. So you have the information you need to say that, yep, there's going to be a problem on this flight. So it might actually be a pretty good forecast. So it's all in the eyes of the user, what is good and what is bad. So different users have different ideas about what makes a forecast good, and it depends on the decision making. And many of you may not be thinking about end users in the work that you're doing, but it may be relevant for other kinds of research reasons. So it turns out the good news is that different verification approaches can be used to measure different kinds of goodness. So we have ways to solve this problem and this conundrum of disconnects between what's good and what's bad. And you'll hear more about those when we talk about the spatial methods in particular. So forecast goodness is a multi-attribute phenomenon. So forecast quality, measuring it directly by verification, is only one aspect of forecast goodness. And the value of forecasts, and Alan Murphy did a lot of work on this, looking at forecast value as a function of of verification results. And it's related to forecast value is related to forecast quality through very complex and nonlinear relationships. And so sometimes you might improve the forecast quality according to certain measures, but it may actually result in a degradation for some users. So this is just an important thing to keep in mind as you're doing forecast evaluation. So there are some approaches that can help mitigate some of this issue. And one is using approaches that are more diagnostic and look at the performance of forecasts from a variety of different approaches. The features-based or other spatial approaches also can help mitigate this issue, where you can tailor what you're really interested in to what your goal is with the forecasts. Also using multiple measures, so rather than relying on one single measure to evaluate forecasts, helps also to give a bigger picture, a more broad picture of what the forecast performance is. And even doing something as simple as looking at multiple thresholds. So if we're looking at precipitation forecasts, maybe looking at a whole bunch of different thresholds from your basic drizzle to heavy rainfall can be a helpful way of representing verification results so that they're meaningful for a wide variety of users. So basically, a simple guide for developing verification studies is we have to consider the users of the forecasts of the verification information and understand what aspects of forecast quality are of interest for them. And typically this means we need to consider multiple aspects. So as you can tell, I'm really pounding in the fact that using a single number to summarize forecast, the quality of forecasts is not the right thing to do. It hides lots of information. So to do this, to follow this guide, the next step would be to develop verification questions that are related to those aspects. And for example, you might have different users might have different kinds of questions that would be of interest. So if you're operating an electric utility, you're interested in, for example, big changes in wind or temperature. City manager, interested in whether there's a severe weather coming and how do I represent the quality of the forecast for that kind of person. And model developers, aviation planners, lots, innumerable kinds of users that you could think about who might have different questions. So then identifying observations would be the next step to represent the event that's being forecast. So when we talk about observations, we talk first, at a basic level, the element. If we're looking at temperature, we need to have observations of temperature. And also matching the temporal resolution of the observations in the forecasts and the spatial resolution and representation. And then identifying thresholds and categories that are relevant for the users. And then there, as I said, one verification measure is generally not enough. So looking at multiple verification attributes that we can evaluate to provide answers to some of these questions. And then selecting measures and graphics that measure and represent the attributes, and really importantly, identify a standard of comparison that provides a reference level of skill. For example, is this forecast better than persistence? Is it better than climatology? Is it better than what we got out of the old model that we're trying to retire? So now I want to talk a little bit more about forecasts and observations. And some of this will seem pretty basic, but it felt important to include it in this talk. So in verification, we generally think of forecasts and observations as being continuous or categorical. Continuous forecasts might be things like temperature, rainfall amount, or if we're looking at a model, a global model looking at 500 millibar height. But we also often want to look at categorical forecasts, both because some things are categorical. That means that they're not on a continuous scale, but they might be dichotomous or multi-category. For example, rain, no rain. Is it going to rain today? Is it not going to rain? strong wind, winds over a certain threshold, or not strong. And often these dichotomous ones are formulated as yes/no forecasts. A multi-category would be more like things like cloud amount or precipitation type. And it may result in creation of categorical forecasts can result from just actually subsetting continuous variables. So we might want to look, for example, at temperature categories, a variety of temperature categories. And so you could take a graph like the one on the right, which looking at temperature, and break it down into temperatures below and above 10 degrees, for example. So other type of forecasts are probabilistic. And probabilistic forecasts can be evaluated in a number of different ways using dichotomous observations, yes/no, precipitation occurrence, multi-category, again, for example, precipitation type, continuous, for example, looking at a distribution of temperatures. The forecast can be a single probability value for dichotomous events, or can be multiple probabilities with a discrete probability distribution for those multiple categories. Or you can have a continuous distribution, for example, what we often get from ensemble predictions. Probability values often, at least when we're looking at forecasters producing forecasters who are producing probability forecasts, might be limited to certain values, for example, multiples of 0.1. So in that case, it becomes almost like a categorical forecast. And then ensemble forecasts, as probably most of you know, are multiple iterations of a continuous or categorical forecast, and they can be transformed into a probability distribution. In this case, the observations, depending on what you're interested in, can be continuous, dichotomous, or multi-category. So matching forecasts and observations is often the most difficult part of the verification process, because most often we have to deal with what observations we have available. We don't have control over the observations. So we need to try as hard as we can to identify observations that represent the forecast event. For example, if we're looking at precipitation accumulation over an hour at a point, we want to be able to have observations at that point where we can record the precipitation accumulation over that hour. And for gridded, the other aspect of this is how do we match if we're looking at a model. A gridded forecast. There are a lot of different options for matching the observations and the forecasts. And two, pretty simple but relevant ways of doing this are looking at point to grid. Do we match the observation to the closest grid point? Or grid to point? Do we interpolate or take the largest value? And it turns out it makes a big difference. The decision that you make in this case can make a big difference in the verification results. So here's an example, a really simple example. We have a grid box and we have an observation in the middle. The point here that's, I'm not sure you can see it, but the point in the middle is where the observation. And if we're looking at 4 grid points, the corners of the square, the way that we do the matching can impact the results of the verification. And just as a simple example, we have here an observation of 10 in the box in the center, and we have points of 20, values of 20, 20, and 20 at most of the 3 out of the 4 boxes, or 3 out of the 4 corners, and a value of 0 at the 1 corner. So if we just match in the upper and the yellow square, if we just match to the nearest grid point, we get a very different, we get a forecast value of 0. So it's a forecast of 0 and an observation of 10. But if we take the average of the 4 grid points, forecast grid points, we get a forecast of 15. So we get quite a bit different result depending on how we do the matching. And this is called representativeness difference. And it will have an effect, obviously, on many verification scores. So final point in this section it's really not advisable to use the model analysis as the verification observation. And we'll talk a little bit more about this. Well, I guess I just coming up next. And the reason is that it's not independent. So if you use your own model's analysis as, it's very convenient because the grid points all match together and it's all great, but there's non-independence. So there are a lot of the model information is being used to create that analysis. So ideally, using observations is a better idea than using model analysis. So as I said, the impact of this non-independence is that you would get better scores that are really not representative of the forecasts of the model's capabilities. So now just a quick discussion about observations. Another sort of ticklish part of doing verification is that observations are not perfect. We know that. If you have instruments almost side by side, they give different information. So it's important to think about observation area error versus the predictability and the forecast error and uncertainty. And actually some of the models in the forecast systems are getting good enough that the observation error is almost, the errors in the models are almost the same as the observation errors. So using different types of observations, as I said, you could have two different observations that would give very different results. So, and just to note, the typical instrument errors for temperature, and this was from a few years ago, about plus or minus 0.1 degree for wind speed, plus or minus 0.5 meters per second, but dependent on the speed. Precipitation gauges plus or minus 0.1 millimeter, but can be up to 50%. So additional issues related to observations are sighting if we're using actual observations, and whether the instruments have been protected appropriately. And in some instances, as I said, forecast errors are becoming very similar to instrument limits. So it becomes a challenge. So observations is just a summary here. Observations are not perfect due to sighting, instrument, and other uncertainties. The errors add to the uncertainty of the verification results. So that's a really important thing to consider in doing verification. So for example, for verification results, and this is a little bit of jargon that we haven't gotten to yet, but some of you are probably familiar with, the root mean squared error can be overestimated. The spread can have create a suggestion that the ensemble is underdispersed with poor reliability and so on. So some of the ways of coping include with this issue, which is a very important one, is quantifying the actual observation errors as much as possible is really important. And there are a few new methods available to take into account observation error that are in the literature now. And having more samples can also help convince you of the reliability of the results. So moving on, I want to talk now about the statistical basis for verification. So we'll get a little bit into statistics. And so any verification activity needs to begin with a thorough examination of the properties of the forecast and the observations. And many statistical and verification tools are based on assumptions of normality using the Gaussian distribution. So it's important to ask the question, is this assumption valid for the data set we're using? And then another question is, does the forecast capture the observed range of the observations? Do the forecast and observed distributions match or agree? And do they have the same mean behavior, variation, and so on? So this is kind of a first step in looking at before doing actual verification studies. So it also turns out looking at the joint marginal and conditional distributions of the forecasts and observations is really useful for understanding how the relationship between the forecasts and observations, which is really what we're trying to do with verification. These distributions can be related to specific summary and performance measures that we also use. So that's the basis is really important for that. And some specific attributes of interest are actually measured directly by these distributions. So just some basic, and probably most of you are familiar with this kind of notation. We think about the marginal distributions, for example, the probability that a random variable x will take on the value of x. And for example, you might think of in June in Reading, what is the probability that the observed minimum temperature is between 10 and 15 degrees? The joint probability then is the probability that both events X and Y occur, where X is the observation, Y is the forecast. So I've got to get that backwards. The forecast is X and the precipitation occurrence is Y. So we get this joint probability, which is that intersection area between A and B in the Venn diagram. So that's our joint probability, which is also obviously pretty relevant for verification. The conditional probability then might be the probability that the minimum temperature is between 10 and 15, given that the forecast is yes, that it's going to rain. So the conditional probability of X given Y. So that is the area in A that's colored. So what does this have to do with verification? It turns out, and this is a pretty obvious thing that really wasn't thought about until the 1990s, that verification really can be represented as a process of evaluating the joint distribution of forecasts and observations, P of F and X. And all of the information, it turns out, regarding forecast observation and their relationship is represented by this distribution, looking at these conditional and marginal distributions. So they show two different conditional, two different ways that you can represent the joint distribution of forecasts and observations, where F is forecasts and X is observations. So you can condition the forecast on the observation or the observation on the forecast. And it turns out that many of the verification measures that we use are based on these kinds of conditional distributions, conditional and marginal distributions. So Murphy and Winkler actually laid this out in a really nice paper, and they described the two different distributions or combination of distributions as the likelihood base rate decomposition and the calibration refinement distribution. So for example, in the bottom, P of X equals X given F equals F is basically a measure of reliability. So I'm not going to go much further into that, but it's really relevant for how we define many verification measures and apply them. So, and even in doing exploratory analysis before doing a verification study, these kinds of things are really good to look at. So here we've got temperature scatter plot for Oslo and Stockholm. And in thinking about the joint distributions, we can represent those as in this case, using scatter plots, other kinds of plots like density plots, 3D histograms, contour plots. And so that's one of the first steps that needs to be done in verifications, looking at those joint distributions. But then you can also look at the marginal distributions, and that's relevant as well. And comparing, for example, the forecast, in this case, the Oslo OBS and Oslo forecast, looking at the box plots and those distributions and the fitted distributions. There are a lot of different ways to represent this, and most of you probably know about some of these stem and leaf plots, histograms, box plots, and so on, including quantile plots, which are a really useful way of representing them. The marginal distributions can be compared. This is looking at marginal distributions with density functions or cumulative distribution on the right there. Looking at, this is a different set of forecasts, but looking at the observed from temperature gauges and the forecasts from the old GFS model. And the cumulative distribution function shows differences between the distributions of the observations and the model as for increasing temperature. And conditional distributions are another really great way to examine data ahead of time. In this case, we show box plots along the diagonal, showing the distributions of observations given particular model forecasts in particular categories. And then basically a smooth version on the right-hand side. So looking at conditional distributions can actually almost be like a verification study. It is a way, for example, in the right-hand side, you can see that there is a bias in the forecasts. Well, you can see it in the left-hand side as well, but it's pretty clear in the smooth version, looking at the different quantile values, because the distributions are lying above the diagonal line there. So now I want to talk just briefly about comparison and inference. And Ian Doleff is going to talk more about the inference part tomorrow, but I just wanted to mention one of the ways we look at relative performance is by a skill score. So we want to know, for example, how much more accurate are my forecasts than what I would get by climatology? How much more accurate are they than the previous model? Or how much more accurate is one model than another model? So it provides a comparison to a standard. So we're using a standard comparison to say which model is my model actually improving things, or my forecast improving things. It's positively oriented, so larger skill score is better. And the really important thing here is that the choice of the standard measure matters a lot. It's a way different thing to compare a forecast to climatology, which is a pretty easy standard to beat, versus comparing a new model to an old model, because they're based on basically the same concepts. So I guess this is a question that we're not going to answer here, but it's something for you to think about, is which standard of comparison would be more difficult to beat, climatology or persistence? Actually, we will answer it. Persistence is much harder to beat. So, but it depends on the forecast. So it depends on whether you're looking at a long-term precipitation forecast or a 6-hour ceiling forecast, for example. So the generic definition of a skill score is that we've got M. M is a verification measure for our set of forecasts, and we have a reference forecast that is something that's reasonable to, it could be the old version of the model, as I said. And MPerf is the perfect measure for a perfect forecast. So you just plug those numbers in and you get the amount of improvement or lack of improvement of a new forecasting system. So for example, for mean squared error, we would include the mean squared error of the forecast minus the reference mean squared error. And then the perfect forecast, the perfect value for mean squared error would be 0. And so essentially we take the difference between the mean squared errors divided by the mean squared error of the reference. So pretty straightforward kind of percent improvement. And there are a lot of different references that can be used. Excuse me. Random forecasts is not a really very useful benchmark. It doesn't have a physical meaning. But persistence might be more relevant. It's a measure of predictability, and it can show added value by running an NWP model. Excuse me again. Sample climate, which would be the current climate, is just looking at, within my data set, can I beat the average forecast? And just if I beat the average observation, essentially. But it's not representative of the long term. So the other option is to look at long-term climatology, which is an easier reference to do better than. and it provides very smooth, smooth results. So have to be careful though in using due representativeness and making sure that we've taken into account things like climate change trends. So a little bit more about comparison and inference. I just want to emphasize that it's really important to measure that uncertainty whenever possible, looking at the uncertainty in the scores and measures. We know that we're taking a sample of forecasts, and so there is uncertainty in the scores simply because that's just a sample. It's not, we're not looking at every possible forecast that ever was made. So the uncertainty arises from sampling variability and observation error, representativeness, and so on. And you can draw erroneous conclusions when you're looking at scoring systems, or when you're looking at verification results, if you don't take into account that uncertainty. And so I think Ian will talk both about the fact that there are parametric and non-parametric ways to look at this. And parametric often or typically depend on a statistical model, while non-parametric are derived from resampling. And I think Ian will be talking about some of that tomorrow. So I just, next little bit here is about verification attributes. The attributes measure different aspects of quality. So it's a way to think about, am I getting the full picture of the performance or the quality of my forecasts. And these attributes measure a range of characteristics that we should consider. And a lot of these are actually directly related to the joint and conditional and marginal distributions of the forecast. So they derive directly from those. And so for example, bias is a very common thing to measure. It's a really like a first and order one thing to evaluate, and it's based on the marginal distributions. Correlation measures overall association, so it's based on the joint distribution of forecasts and observations. Accuracy is often typically based on differences between forecasts and observations, and so it's also based on the joint distribution. Calibration measures the conditional bias in the forecasts. And so it's based on the conditional distributions of forecasts given observations. Discrimination is the degree to which forecasts discriminate between different observations. And so it's also based on conditional distributions. So this is, I think, really emphasizes again what the importance of understanding these distributions is and the distributional basis of verification. So let's just for a minute talk about some desirable characteristics of verification measures. And I think this is the slide that I meant to take out. So we're going to talk about meta verification, which is a term that was first used by Alan Murphy in a paper in 1996. It's basically meta verification is the idea of looking at desirable properties of verification measures. One of them, to me, a really important one is just statistical validity. Are we doing things that make sense from a statistical perspective? Are we, appropriately computing the scores and their uncertainty? Consistency was proposed by Murphy in 1993, and it basically talks about the appropriate representation of forecast uncertainty for using the use, for example, using probabilities. And Murphy was a big proponent of probabilistic forecasts. And I think his idea is that you can only produce consistent forecasts if you actually directly represent the uncertainty in the forecast. Propriety goes back a little bit further. It indicates it's a measuring whether the forecaster is rewarded for representing probabilities choosing probability values that correspond to his or her true beliefs. So not hedging it because you think you might get a better score, for example. So it prevents you from wanting to hedge. Equitability refers to the idea that unskilled forecasts of any kind should receive the same expected score. And it turns out that no scores achieve this in a rigorous sense. In fact, most scores are sensitive, for example, to bias or event frequency. So I'm not going to say more about this because it's an important thing to have in mind, but and thinking about as you choose scores, but it's not applied directly very often. And we have some idea in the literature about which scores meet these or approximately meet these criteria. So just to summarize, I want to first emphasize that if a forecast is being formulated, they should be verified. All forecasts should be verified. If it's worth forecasting, it's worth verifying. But it means that you have to formulate the forecast so that they can be verifiable. And sometimes we do this all the time, forecasting in places where we don't have good observations, so we can't really verify them. So, and I know this is not a truth that we can hold to or a rule that we can hold to all the time, but as much as possible, we should have a way to verify forecasts that we're producing. Stratification and aggregation, I haven't talked about this, but aggregation is good for helping to increase sample size so you have more robust statistics. But when you aggregate too much, you can hide important aspects of performance. And in fact, you can get misleading information. For example, the most common regime may dominate the results, and you might not be able to see variations in performance. So stratifying as much as possible into meaningful and homogeneous subgroups is really important. Observations, I didn't say this before, but observations are observations and they are not the truth. There is no such thing as truth in observations. Observations are usually more true than a model analysis, at least, and they're more independent. But when possible, we should take into account observation uncertainty. So for example, just even looking at how well adjacent observations match each other. So finally, some key things to think about is who wants to know when we're developing a verification study, who are we designing it for? And what does that user care about? What kind of parameter are we looking at? And so on. What are the characteristics of the observations, their quality and uncertainty? And what are the appropriate methods that can help us put together those observations and forecasts? And I think then understanding why are we doing the verification? What is it we really want to learn from a verification study? And then how do you present results? For example, do we stratify it? Do we aggregate it? Do we need to summarize things for a management group? And what's the best way to do that? So then deciding which methods and metrics are appropriate once we understand all these other things. How can we meet these expectations? And what methods do we really need to evaluate, including bias, event frequency, sample size, and so on. So now I'm just going to end here. I included a few relevant references and links that you may want to take a look at. I've also included a few optional exercises that follow this. So if you're interested in trying to take a look at these, one of them involves looking at box plots of error distributions. There's a contingency table example to look at and see what you can learn from it. And what I call a discrimination diagram example. And the slides for these exercises explain what they are. If any of you wanted to look at these, I'll be in the group tomorrow in the open session, the drop-in session at, let's see, 1100 BST. So yeah, I think that's right. No, actually 1400 BST. So if you want to look at those exercises or you want to discuss anything, I will be there tomorrow. Or if there are any questions in addition to what we talk about today about my presentation, please don't hesitate to ask those tomorrow or by email as well. Thank you very much.
Okay, thanks, Barb. It's an interesting talk, as usual. There's no activity in the chat at all, actually. Chat's been very quiet, but does anybody have a question for Barb. I can scan them.
Oh, I've got to stop sharing here, but I haven't been able to find my stop meeting controls. There we go. Okay, here we go.
I don't see any hands up either. No, I don't think so.
Um,
Well, I can,
Oh, Ted.
oh, actually,
There's-
well, we have a question, so let the real question come in, but if, I also have a more philosophical one, but maybe you should go to the chat, there's just been one posted.
Yeah, I see that. It says, how can we extrapolate verification principle for climate projection? And there has been some work done on that. I think that the challenge is, of course, that for climate projections, especially if you're going into the future, we don't have observations. So the easiest way to do that, of course, is to do hindcasts and then look at them. But somebody else in the group may have a suggestion about that. Anybody? So in principle, Barbara has her hand raised. You want to say something,
See
Barbara? You've done
another-
this kind of work.
Here's another question.
Well, can we let Barbara ask her?
Yes,
think
actually, I
Barb-
wanted to comment about the climate
That'd be
projection.
good.
It's because climate, if you project something in 100 years, you obviously don't have the observations for 100 years, right? Ahead. So you can't really verify directly the climate projections, but what you can do, you can verify them in weather mode. So you run your climate model on a present state, okay? But still accounting on the fact that the processes in the future are likely not to be the same as the processes in the present. So it's really more the process verification that you want to look at and target the processes that are going to affect the future. So it's a very complex, open question, this one, that probably we are going to discuss more in the last day on Friday.
Right.
That's my
Yeah, that's a good way of putting it, Barbara. I think I was kind of trying to say the same thing, but not quite getting it. So that's good. Thank you.
Can I explain a little bit, Barbara, my question?
Yes, sure.
Okay, concerning the how can we extrapolate the verification principle for climate projection, what I want to say, before we project a climate, we have to verify with the observation data. For example, with 13 years. So how can we apply this verification principle for the climate projection? That is my questions. With the observed value of either precipitation or temperature. But the year, maybe it will take 13 years, starting maybe from today backwards 13 years. That's what I want to say. Thank you.
So Barbara, do you want to respond to that? Yeah, I think that's basically what Barbara was suggesting. Is that you take information from the current climate and
I guess so. I haven't thought of it deeply, but one thing also I would consider is to look at analogs. So for
Right.
example, you look at, regions, say latitudes that are more, like lower latitude, for example, and then you apply that type of, processes to a higher latitude as an example. So these are all good, I'm noting them down, good discussion topics for Friday.
yeah.
There is another one, and it's very interesting about the impact of the horizontal interpolation methods on verifications. part.
Yeah, and I think that I was referring to that in the slide I showed, but I think that we have to, the interpolation methods are hugely important in how we do that. And the example I showed where you go point to grid to point or versus point to grid makes a huge difference. So and I think it depends on what your goal is with the verification. So it does make a huge difference, but it depends on what your goal is in the verification. Whether you're really trying to verify what is the forecast at that point, or are we trying to get just sort of an average overall view of how the model performs. So, I mean, it definitely has a huge impact, or it can have a huge impact depending on, for example, for temperature, it may not be as huge of an impact, but if you're looking at precipitation, it can be very, very large.
Yes. Okay, we have another question. How do we exclude the impact of data assimilation when evaluating an operational model?
Well, I guess the question is whether you want to exclude it, because data assimilation is fundamental to the performance of a model, and many models won't do very well unless you're doing the assimilation. So what I know, I think, and I may not be completely understanding the question, but I think what we want to do often is evaluate the whole modeling system, not just the model itself, but the data, including all the components of it, including the data assimilation. So if you're doing, if you're looking at, say, a 12-hour forecast or a 24-hour forecast, then the impact of the data assimilation is less important. It's not going to show up as a significant factor, I think. So if I'm understanding the question correctly.
Yeah, that's a good point. I think that the longer the forecast projection, the less impact the data assimilation would have on verification.
But even still, the data assimilation is important for the short term, because it's, it seems we're not mixing in old observations when we're doing the verification. We're taking the observations that are available at the valid time of the model. So.
Yeah. And the effect of data assimilation and with respect to verification is that it tends to nudge the observation field towards the model climatology.
Mm-hmm.
So it essentially biases it's not independent, in other words, anymore, the model. So that's one reason we say that we should not use data assimilation at all, information in verification as observation.
Right, exactly.
But if you do use it, the question is how to exclude the impact. I'm not quite sure I would know how to do that, other than just not using assimilated data, but use observations and verify only where you have observations.
Exactly. That's, I guess, a really good point, Lori, that we do, it's preferable if possible to just use observations. So Karen has a hand raised.
Yeah, so I was wondering another way of reading that question, instead of using the word exclude, to make it less categorical, how would one go to measure the impact of data assimilation, the contribution to skill from data assimilation? So you're right, that contribution falls off the longer the forecast horizon is. But it's still an interesting question. How would one go about quantifying?
I think people have done that. You can run the model without the assimilation. So it's just a pure model and do that comparison. And it is true that so for example, if you're assimilating radar observations, the contribution of those radar observations falls off very quickly. So Ted had a comment, Lori.
Yeah, there's a comment from Ted here, I guess going back to the climate question. A suggestion could be to compare joint probabilities. For example, precipitation in a certain region conditioned on the phase of ENSO. That would be an example of a process-oriented comparison.
Yeah, that
Right.
makes a lot of sense.
I guess we're at the hour, but maybe I'll just plant a seed, Barbara, because I was struck by the fact that the title of the first workshop, if I got it right, was meaningful.
Yeah.
I was wondering what you meant by that, because it's a term that comes up in climate science too. How do we make climate information meaningful? I don't know if you want to quickly elaborate on that. Or
Yeah, so the timing of that workshop was interesting. It was in 2002, and verification really was, nobody was really putting a lot of research effort into it. There were a few of us, as you saw in the picture, but everybody was just using root mean squared error and leaving it at that when they were evaluating the models, and they were finding that we're not getting any useful information about how to improve the forecast. So I think that was the main idea behind it, was to provide information that could be useful for improving forecasts or for use of forecasts. And it was actually sponsored by an aviation program to try to get better forecasts, verification information for aviation forecasts, aviation weather forecasts. So we were lucky to have that sponsorship, because we actually made it a much broader workshop than that, and brought together all these people who had been thinking about these things. So that's what we meant by meaningful. It's just how to provide information that can be used to improve forecasts or for users. Barbara, you have a hand raised, and I know we're at the end of the time, but we're past the end of the time.
Yes, I wanted to say that there is some verification conditioning on weather regimes, and it's absolutely very relevant, and is used especially in seasonal forecasts, but not only. We are, for example, looking at, for the polar regions, conditioning on the phases of the Arctic oscillations. Is interesting, to understand, in certain regions, when there is a weak or strong, it's like oscillations, you see different, weather exchanges between mid latitudes and polar regions, for example. So and there is also some error tracking techniques. It's more on the dynamical way, but you go backward, essentially. You try to identify regions where the error comes from. That's also related to the data assimilation question, because also you identify regions where you might need to assimilate more observations, essentially. So I just wanted to put that.
Great. That's a really good point.
Okay, I don't see any other hands. And messages are at the bottom of the list for the chat. So I guess we're at the end of this session. Thanks again, Barb.
You're welcome.
Okay, I guess we continue right in, or should we take a break?
I think we can go right in if that's okay.
Yeah, okay. So I'm up next. And so it's the time to introduce the projects. Let me share my screen. Okay. Can everybody see that?
Yep.
Yeah. Okay. So now I'll just interview. Okay. So yeah, so the projects, there are 19 of you who are involved in the projects, and you've all received the descriptions. of the projects and chosen the ones that you prefer. Fortunately, we were able to give almost all of you the ones that you asked for as your first choice. I'll start with the goal of the projects, following along from Barb's suggestion. It's an opportunity for you to experiment with verification on real meteorological data. It's all point data. This is not spatial verification. We thought about adding a spatial verification project, but technically that would have been too difficult. So the projects are all based on point meteorological observations. But we wanted the focus to be on the interpretation, to give you a chance to contemplate and work on what the results actually mean. And we're kind of hoping that your interpretations will be an important part of your presentations on Friday. All the projects are comparative. Whoops. In the sense that there's one observation which is matched, the matching has been done to, I think in all cases there are 3 models involved. So you have 3 forecasts verifying at the same time and location as the observation, as the verifying observation. So that gives you a chance to interpret the scores through a comparison between the one model and the other models. So that's one thing that we hope to see in the presentations as well. Most of the data, the other thing is so that the projects can really focus on getting results quickly, because we only have a few days, and interpreting those results and preparing the presentation. Most of the data setup has been done. The matching, which usually takes a long time in actual forecast practice, verification practice, usually it's the most complicated part of the project is putting the data together, matching the forecast and the observations, because they come from very different sources with very different characteristics. But that's been done. So the data sets you've been given are already matched. And so each row, for example, is one case or one event with the observation and all the matching forecasts in the same row. The observations all come from the WMO Global Telecommunication System, the GTS, which is the backbone of global operational forecasting. And they're available in near real time globally. And they've just been collected for the purpose of these projects. The forecasts all come from NWP Center's operational models. So they're actually running models that run daily in real time. The forecasts are deterministic. In other words, they apply at a particular point in time, point in location, in space and time. That's projects 2 and 3. Project 1 has ensemble forecasts, which are also deterministic in a sense, but they're deterministic, run from slightly different versions of the model or slightly different initial conditions. And so there's lots of potential for interpretation in order to set up a project. So those of you doing project 1 maybe in some sense have the biggest challenge and the most opportunities for how you actually prepare the verification and present the results. Project 4 is a little bit different. The data comes from Demeter, which is a project focused on seasonal forecasting methods, models. Again, there are 3 models involved, not operationally run. In this case, it was a research project. And the observations for that one come from an analysis rather than from, and for a particular point, however, in the middle of the ocean. In your project descriptions, I made suggestions about how to approach it, but there are quite a few different things you could do with the data sets, which I hope will make it more fun, because there's lots of opportunities, and many things are legitimate to do the verification. But there are a couple of things we really want you to do for pretty much for sure. The first step in verification, as Barb said, is always take a good look at the data. So the best way to do that is graphically plot the data in forecast observation plots. We're amazed at how often bad data tends to find its way into the data sets. And usually if there is bad data, you'll see it right away when you do a plot, you know, like a missing value of -99 will show up as if it's a legitimate temperature, and it'll be very obvious. So that check should be done. We think we've gotten rid of all the bad data. The data that is not useful has been taken out. But just in case we haven't, this first step is important. And you'll also, and especially if you do a separate plot for each of the models involved, which are all compared to the same observations, you'll very quickly get an idea of how the distribution, the joint distribution of forecast and observations looks in different cases. And you may see some of the differences among the models already just by doing that. So since the projects are all comparative in nature, you have 3 model forecasts verifying at the same time in places, then it's good to do as one of your goals to figure out which model is better and why, at least for some forecast verification that you set up. We also, since it is comparative, we also ask you to do your best to use confidence limits to assess the comparative results from the different, maybe they're not very different, the 3 models, and you can't prove from the data set you have that they're sufficiently different to be statistically significant. But other than those 2 things, it's up to each group to design your experiment following verification principles. Barb talked quite a bit about considering user needs. You can pretend that you're a modeler, you can pretend that you're a wind energy manager, and focus on those aspects which are important or would be important to you in one of those situations. Barb also mentioned a couple of times the need for multiple verification measures to fully assess the quality. Some verification measures are inherently incomplete and they can be misleading if they're presented by themselves. So they need to be paired with other measures which make up for the limitations. And then we ask you, each group, to prepare a presentation for Friday afternoon. We don't mind how many of you speak. You can give it to one person to do. You can each say something. The goal is 15 minutes, to have 15 minutes to present what you did, what your results are, and what they mean in terms of your chosen user community. If you're a modeler, for example, you might look at different aspects of the model over a different range or over different forecast projection times. The data has been organized separately by forecast projection in most cases. So you can see how the model quality changes from one forecast to the other, one forecast projection to another. And then then you should draw some conclusions about which model's better, at least for the forecast experiment that you carried out in your group. You can do more than one if you want, if you have time, more than one different experiment, that's up to you. So I wanted to add a little bit to what Barb talked about, the forecast attributes. And this is in the form of a kind of summary sheet. It's, I guess, a bit unusual to try and summarize the whole set of verification tools for point forecasts before we even talk about them, really. But this you might find useful during the project to decide which measures to use and when. So this is mainly from a paper from Alan Murphy, who's been mentioned already, around 1993. I think he wrote it on what forecast goodness means. Barb talked about attributes. So I list here 9 attributes of forecasts, which can be assessed. And the thing to realize is that whether the variable is of a continuous nature, a categorical, or a probability forecast, the attributes are measured the same thing. The scores are called by different names. They're calculated a little bit differently to take into account the format of the forecast, but you're measuring the same attribute. For example, if you're doing a Breyer score for a probability forecast, that's just the mean squared error. So it's measuring the same accuracy attribute as the mean squared error does for a continuous forecast variable. So I'm not going to do this in detail, but the attributes here are categorized, are color coded. The first 4 are attributes which don't imply any particular stratification of the joint distribution of forecasts and observations. They're kind of general in a sense. So you have the bias, you have the association, which is correlation mainly. You have accuracy scores, which are general. It's just a comparison between the individual pairs of observations and forecasts. And then you have relevant scores on the right-hand side, the right-hand 3 columns for each type of variable. So you'll have lectures on these on continuous, categorical, and probability. I think they all occur tomorrow. And then for project 4, which is special considerations for longer range forecasts, seasonal forecasts in the case of project 4, that lecture is the next day. I think it's Wednesday. Caio Coelho will give that talk. So the first 4 of these coded red are general with no stratification, no conditioning of the distribution, joint distribution. The next 3 that are in blue are conditioning according to the forecast. So it implies a stratification of the data set, the joint distribution, by probability. And the most common is to divide the forecast into deciles of probabilities and then assess the model or the forecast on that basis. So you have the reliability diagram, for instance, resolution and sharpness quantities. And then the other 2 in green are related to the stratification of the sample according to the observation. So you have discrimination. There you have the Hansen-Keeper score, for example, in categorical prediction, which is just the hit rate minus the false alarm rate. You have the EDI and the SEDI, which are nonlinear functions of the hit rate and the false alarm rate. And you have the relative operating characteristic curve, which also is a plot, basically, the hit rate and the false alarm rate for different thresholds of the variable. So those are all 3 all measure the same attribute of the forecast, which is the ability to discriminate between occurrences and non-occurrences of an event, for example. I'll mention just sharpness. Sharpness is just the variance of forecast. It's just the variability of the forecast alone. It doesn't have anything to do with the observations. And on the other hand, in the case of the observations, uncertainty is the variability of observations as described by the distribution of observations. So for instance, for a continuous variable, you'd have the observation variance or standard deviation. For a probability forecast, you have the variance of the probability, or the variance of the observations, occurrence or non-occurrence of the event, which are usually binary. So I think maybe I don't need to say any more about this now, but I'm happy to take any questions if you have any about the projects. Gabriel is going to come on after this for a few minutes to talk about the technical details of reading the data, etc. So there's a question.
I don't think there are any questions in the chat, Laurie.
Okay,
Paste.
I see a hand up.
There's a raised
Ac-
hand.
Yeah, raise hand, Akshay Kulkarni.
Yes, sir.
Yes, please.
So how the actually groups you are going to divide or decide, like?
Well, the groups have been set for the 19 people who are going to do the group projects. They should know already because I have set up the groups already. I don't recognize your name as having been on that list.
Okay.
I'll
So
just, I could just maybe quickly say, this is Ted Shepard. Yeah, so we'd asked who wished to be part of these project groups, but of course the projects, anybody, I think, Laura, you could confirm, is, you know, free to look at the projects and play around with things and so on.
sure. Yeah,
But we have certain preset groups that are already there. So I'm sorry if you had wanted to be part of it and weren't, but anybody can look at these and do their own experiments as well and so on.
Okay.
Okay.
Fine. Thank you.
Don't see any. I should stop sharing my screen. Okay, I don't see any other raised hands. So maybe we could carry on with Gabriel if you want to talk about the technical side.
Yeah, sure. Thanks, Laurie. Yeah, it's going to be certainly very, very brief. So there's only a few things I need to talk about. I try and share my screen. Oh, I'm not allowed to share my screen, apparently. I
Oh,
don't know if there's a technical person in the call that could.
Yeah, we have a host, but Barsh, I guess, are you still there? Barsha?
I think you're a host that can, maybe if you go on the bottom, there is like the share screen option.
Yeah.
Maybe there is an option that you can allow other people to share,
Oh, you think
perhaps.
so?
I'm not sure, but
Asked or something. I'm not sure I can. Just a second.
there's when I'm doing my own calls, there's usually an option saying multiple participants can share at the same time or something. That kind of.
yeah,
Oh, yeah.
I had that too.
So I just clicked that. Now what happens next?
No, let me
Does
see.
that help?
Oh, now I'm allowed. Yes.
Okay, good.
Thanks. That's sorted it. Okay, I will try and share my browser screen and let's see. Okay, can you all see my screen?
Yeah.
Yeah.
Okay, thanks. So I'm assuming you all got Laura's email with the link for this repository. So MP-CDT forecast verification, and we'll be starting some of the things from summer school here, such as the lecture notes and the project information. So if you want to download, I recommend you should just use git clone and the URL of the repository so you can get everything at the same time. Alternatively, if you don't have Git or is not comfortable with the terminal, you can download manually. For example, you can go to the lecture notes folder, then Barbara Brown, and you can open the PDF here and perhaps download it manually clicking on the link. The same can be done with the data sets. So for example, we have project 1 here, and all projects are more or less separated or organized in the same way. So we have a description file provided by Laurie. So with all the information required for the project, you can download that manually as well, or by doing the git clone procedure. We have a source folder where I've provided some analysis examples. So there is this raw data manipulation script in most projects, where it's just a Python script to kind of simplify the data provided by Laurie, the raw data, and make it easier for you. And for example, here I have this analysis example script in R. It's just a very simple script to read the data and calculate the mean square error. So just to give you a start. And the other projects are just the same, more or less the same organization. Some projects only have a raw data folder because there's no need to do anything to organize data. The raw data is just fine. And all of them have the description that you can download. Another thing is that there are some recommended Python and R packages. I was hoping to get some recommendations for MATLAB, but we got some recommendations for Python and R. So for Python, and this is the tool that I'm more familiar with and I can help most with. So some people may want to choose Python, and if they do so, I really recommend Xarray. It's a tool similar to Pandas to organize multidimensional data sets. And I'm recommending Xarray here because of this package, XSkillScore. That is a very interesting library with all or most of the metrics that will be introduced in this summer school. So you don't need to implement anything. You just need to read your data, put that into an Xarray data array, and then use this library here to calculate the metrics that you want. We have a few recommendations in R as well. So Spatial VX and a package called Verification. I think these were mentioned in one of the talks. So I'm sure you can find the instructions to download and install it in this link. And the last thing I wanted to say is that I will be providing, or at least trying to provide some help for the projects, especially if you're using Python, but I can get myself around R as well. So if you want some basic, if you have some basic questions in R, I can help with too. So the hours that I'm proposing for helping with the projects is from Tuesday to Thursday, I think are the relevant days, because obviously today you'll be just starting dealing with the data, and the presentation is on Thursday, so I think on Friday. So I think from Tuesday to Thursday is a good time for the sessions. And it is a separate Zoom link that I will be sending in an email to the participants of the project. And I was thinking to have 1 hour to be available for 1 hour after the last session of the day. So 5 British summer time. So starting from 5, I will be online in a Zoom call and be available to try and help with the projects. So I think that's all I had to say. I don't know if I missed something, but if it's all clear. Do you have anything to add, Laurie?
I don't think so, except to say that I'm around, certainly by email. You can email me at any time, and to answer questions on the verification topics. And I'll be, I think I'm on one of the help sessions on, I think it's Wednesday at 14. Yeah, 14, yes, 1400, 2 o'clock. So that's another opportunity for direct contact. But I will certainly answer as quickly as I can any questions you have via email.
And the same goes for me. If you have Python or R questions and you want to ask something out of the hours I just said, you can email me and I try and help.
Okay, so I don't think I see any more questions. I don't see anything further in the chat. Okay, so I guess, oh,
So-
Karen,
Sorry, Laurie, maybe my audio dropped off for a minute. Maybe I missed it, but there was a question about how do the students organize themselves? Did you see that one? Where to find names,
oh,
etc.
I didn't see that one.
Well, is that, yeah, but I think that's,
So sorry, I didn't get how are the groups organized, where to find names, etc.
The group list of students in doing each project was sent away, so it was sent to them. I didn't copy the teachers, but I can send that to you if you want to see who's doing which project, for example. But there are five people for one, or 5 on 2, 5 on 3, and 4 are doing number 4.
so,
Should I do that,
Yeah.
Ted? Should I send that information?
well,
to
I think the yeah, I guess there's a few people, oh, you know, I'll just say, I'm sorry if there was some confusion. When we had sent out the announcement, we had indicated that there was the lectures, and we had also anticipated some small assignments connected with the lectures. For example, Barbara gave a few this afternoon. But then we also mentioned the group projects, and we asked people to indicate if they wish to do that. And we only had 19. I guess there's questions about whether there can be new groups. I think we can't manage new groups in terms of the structure that we have in terms of the presentations and everything at this point, because we had not we thought we could manage something like 15 to 20, and we got 19, so that's basically about right. I think we can't really manage. Well, you only have the 4 projects, and but certainly everybody has access to the files. If people want to try to, I don't know quite what to say, and in terms of a new group, in terms of the formal activity on Friday afternoon. Yeah, I'm not sure about all the comments. I'm not, because I don't think we can manage additional groups to be part of the formal activity, but there seems to be a lot of interest now in the groups.
Right.
I mean, one thing is whether, if I think, I shouldn't put Gabriel on the spot, but if other people want to be trying things out, I think that's certainly fine. And you could certainly feel free to email Laurie or Gabriel, and if they get overwhelmed, they can just say so. But I think at this point, I can't quite see how we could, well, maybe we can talk about this offline, but I can't quite see how we could fit more in on Friday. So I'm sorry if there was misunderstanding in the, there seems to be a lot of interest in the projects now, more than we had realized when we said more than
Right. Yeah, did a selling job, I guess, or something. Yeah.
Yeah, well, maybe it was the prices.
Yeah.
We'll have to discuss maybe offline a bit. Yeah, we can just. So I think we can try to see if there's something else, some way that we could help to expand this training opportunity. If not right now, in a subsequent time or something like that. But yeah. Sorry, I don't have a better answer. I mean, because the groups are going to work together, and obviously they have to self-organize among the 4 or 5 people in each group.
I concur with Ted. We actually specified it into the announcements, and we had few people telling us that they were interested, so we organized the project. It's a bit difficult to do it on the fly now, but I will encourage to people that are interested in doing this project maybe to drop an email either to me or to Laurie, we can cluster you and you can give it a try. The timetable now is set. So for Friday, we won't introduce other presentations, I think. But still, they are interesting projects and you can have a look at that and, have maybe questions on that and we can take them maybe offline, but maybe not into the school schedule that is already quite dense, I would say. But I'm pleased actually that people are more interested into the projects. People are definitely encouraged to look at the data and give it a try. And we can take it offline, maybe on email, something like that.
Yeah, the data sets actually are small enough that I can send data sets to people by email if they want to try themselves to do the projects. I mean, I don't see why we couldn't do that. And
they are on the GitHub, so you don't, people can download it, right?
Yeah, everyone can access the GitHub. It's in the timetable, and I've also put the
okay, the projects are available to everybody in the GitHub.
Yeah, it's all the same.
Okay, it's all the same GitHub. Okay. Yeah.
So I guess the only question is, maybe I misread the original question. If the students know who all the other students are,
they do.
Right. So they can identify who's in a project and who's not, and all the ones who are not in a project could conceivably just get together and start working together. Is that true?
Yeah.
I could on their own initiative.
That could be their own group right there, right? Just start their own group.
Yeah. I mean, what we can't really do, as Barbara said, is schedule them for a presentation on Friday. That's, we have limited time for that. So.
Yeah, so I'm just repeating what I think we all said, that the students could just get together and start working on the projects on their own. The only problem is that they won't be able to have a presentation. I'm speaking to the students basically here.
I'm happy to answer questions from anybody. Yeah, it doesn't. It's not. I'm happy to not limit it. Well, not limit questions to answering questions to the project participants, the official ones.
Yeah.
And anybody who's has a question, I'll try to answer it.
But I think if I understood, Barbara, if people just email you if they're interested, is that okay? If people that are not formally part of a project, and you could try to, I don't know how we organize people. That would be. Okay, well, Gita Nain has just offered to be a point of contact. If you're interested, if you're not already in a group and you wish to be involved in trying to work together. Thanks, Gita.
Okay, I see. Okay.
Well, that's amazing. Great. A lot of interest in the projects. You never will.
Yeah, that's nice. It's good.
I just sent out an email to the project participants, the official ones, with the Zoom link for my session and the times that I'll be available. But maybe if Ted or Barbara want to forward that to all the students in the school, and I don't know, or the students that form these non-participant groups, I'm also happy to try and help everyone that's interested. So
okay,
it's up to you, Ted, or if you think that's a good idea.
Well, maybe let's talk about that. Sorry, we'll circulate things maybe separately. I think we're gonna have to do some thinking here. But thanks for that, Gabriel.
Okay.
Okay. I think
we're done, I guess.
Yeah.
Yeah.
All right, everybody. So I think the next item on the agenda is the lecture at 10 a.m. British time tomorrow. with Barbara Casati. All right, thank you, everybody then. I guess we're done.
Okay, thanks.
Thank you.
See everyone.